Hi guys, we're going to talk about energy transformations and conservations. You should try and say that. Energy transformations and conservations. I know it will be weird to say that out loud, but just trying to help you learn those two words because that's what the next quarter will be all about. So, energy transformations. To ask you a few questions before we get started into taking our notes. What does flowing water have to do with electricity? In the picture, you can see what is called a dam. You already may know that mechanical energy of moving water can be transformed into electrical energy. So, mechanical energy, if you remember from our notes, water was under the examples for mechanical energy. And why is that? Because water can move and stop. It has kinetic and potential energy. And if you remember from our notes and our discussion in class, kinetic energy is the energy of motion and potential energy is stored energy. So it's going to move at some point, but it's just not moving yet. And the dam stops the water, but it allows some water to flow through. And that water that flows through is called mechanical energy. And that mechanical energy does a lot of work in a generator, which is inside, and it turns it into electrical energy. So energy is never lost, it's just transformed from one type of energy to another. It's pretty cool. Most forms of energy can be transformed into other forms. A change from one form of energy to another is called an energy transformation. Some energy changes involve single transformations, while others involve many transformations. And to be honest, most things that you see moving and doing work is a result of many transformations of energy. So single transformations. Sometimes one form of energy needs to be transformed into another to get work done. For example, a toaster transforms electrical energy to thermal energy to toast your bread. A cell phone transformation involves electrical energy to electromagnetic energy that travels to other phones. Your body transforms the chemical energy in your food to mechanical energy you need to move your muscles. Chemical energy in food is also transformed to the thermal energy your body uses to maintain its temperature. Multiple transformations, so many. And remember, we wrote this word down as one of our vocabulary words. Multiple means many. Often, a series of energy transformations is needed to do work. For example, the mechanical energy used to strike a match is transformed first to thermal energy. The thermal energy causes the particles in the match to release stored chemical energy, which is transformed to thermal energy and the electromagnetic energy you see as light. In a car engine, another series of energy conversions occur. Electrical energy produces a spark. The thermal energy of the spark releases chemical energy in the fuel, the gasoline. Remember when we had this CER in Mr. Rife's class, this is explaining this. So if you didn't understand it then, maybe this can help you. So the fuel's chemical energy in turn becomes thermal energy. So the gasoline is chemical energy and it turns into thermal energy. Thermal energy, remember, is the heat energy, is converted to mechanical energy used to move the car and to electrical engine energy to produce more sparks to continue to go. Transformations between potential and kinetic energy. Now we'll spend quite a bit of time in Mr. Rife's class talking about this, and so we'll spend quite a bit of time talking about it in our ELD class. This is one of the most common energy transformations in the transformation between potential and kinetic energy. In waterfalls, such as Niagara Falls, potential energy is transformed to kinetic energy. The water at the top of the fall has gravitational potential energy. As the water plunges, falls down, its velocity increases. Its potential energy becomes kinetic energy. That's the transformation. Look at this juggler. Any object that rises or falls experiences a change in kinetic and gravitational potential energy, like on a roller coaster going up and down. Look at the orange in the picture on the right. When it moves, the orange has kinetic energy. As it rises, it slows down. Its potential energy increases as its kinetic energy decreases. They have an inverse relationship, potential energy and kinetic energy. At the highest point in its path, it stops moving. Since there is no motion, the orange no longer has kinetic energy, but it does have potential energy. As the orange falls, the energy transformation is reversed. Kinetic energy increases while potential energy decreases. Think about the example in Mr. Rife's class with the pendulum. When he was swinging the brass circles back and forth. That's a pendulum. Also looks like a clock. In a pendulum, a continuous transformation between kinetic and potential energy takes place. At the highest point in its swing, the pendulum in figure 12 down here has no movement, so it only has gravitational potential energy. As it swings downward, it speeds up. Its potential energy is transformed to kinetic energy. The pendulum is at its greatest speed at the bottom of its swing. There, all its energy is kinetic energy, moving energy. As the pendulum swings to the other side, its height increases. The pendulum regains gravitational potential energy and loses kinetic energy. At the top of its swing, it comes to a stop again, and so the pattern of energy transformation continues to kinetic, potential, potential to kinetic. Now, a pole vault, if you look at the picture closely, that is an Olympic event. You stick a pole in the ground and it flings your body forward. A pole vaulter transforms kinetic energy to elastic potential energy. Elastic potential energy is like a spring. When you close it tight and release it, it moves really fast, which then becomes gravitational potential energy. The pole vaulter has, you see in figure 13 here, has kinetic energy as he runs forward. When the pole vaulter plants the pole to jump, his velocity decreases, so his speed decreases, and the pole bends. His kinetic, his moving energy, is transformed to elastic potential energy in the pole. As the pole straightens out, the pole vaulter is lifted high into the air. The elastic potential energy of the pole is transformed to the gravitational potential energy of the pole vaulter. Once he is over the bar, the pole vaulter's gravitational potential energy is transformed back into kinetic energy as he falls toward the safety cushion. Now, if you think about conservation of energy, so that's how energy is held or conserved. If you set a spinning top in motion, and a spinning top is right there on the picture, it's a toy, will the top remain in motion forever? Of course not. What happens to its energy? Is the energy destroyed? No. According to the law of conservation of energy, when one form of energy is transformed to another, no energy is destroyed in the process. According to the law of conservation of energy, energy cannot be created or destroyed. If you recall, on the first day of fourth quarter, we talked about this. I said that the same amount of energy that is on the planet today is the same amount of energy that was 1 billion years ago. The total amount of energy is the same before and after any transformation. If you add up all the new forms of energy after a transformation, all of the original energy will be accounted for. It will be equal. So, what happens to the energy at the top? Where did that energy go? As the top spins, it encounters friction. If you recall from quarter 3, friction slows things down. Whenever a moving object experiences friction, some of its kinetic energy is transformed into thermal energy, heat energy. So, the mechanical energy of the spinning top is transformed to thermal energy. The top slows and eventually falls on its side, but its energy is not destroyed. It is just transformed. The fact that friction transforms mechanical energy to thermal energy should not surprise you. The fact that friction transforms mechanical energy to thermal energy explains why no machine is 100% efficient. It means that it doesn't work perfectly. You may recall that the output work of any real machine is always less than the input work. This reduced efficiency occurs because some mechanical energy is always transformed into thermal energy due to friction.